So today's topic is called equations of motion, or kinematic equations. And as the name suggests, we're going to be working with a group of equations to solve problems that usually are a little bit complex. So many students get scared with this topic and do their worst in this topic out of all of physics. But that is because they read the question, it looks intimidating, and they get scared before they give themselves a chance to try. So what I'm going to try to do today is to teach you a recipe that you can follow, a list of instructions, so that you know how to attack one of these problems without getting intimidated by it. So first I'm going to introduce the variables that are in the equations and the equations themselves. So they are just a less specific way to write the ones from last class, and the variables are the same. So the variables are the following. We have initial speed, which is written as v in a small 0 or o. This is initial speed. And it's always given in units of meters per second. We also have final speed, which is written just as v without anything beside it. And this is called final speed. It's also speed, so it's also given in units of meters per second. Then we have acceleration, which is given in units of meters per second squared. Like the acceleration due to gravity, but this class, because we're not only looking at objects falling due to gravity, but accelerating because of many different reasons, we're not going to give this always the value of 9.8. It might be 1, 0.2, 1,000. It doesn't necessarily have to be 9.8. We also have our time t, which is given in seconds. And finally, we have our distance. Usually in Khan Academy at least, it's given not only as x, but as delta x. So delta just means change in something. So delta x means like that change in position. If you were here, the delta x is how much you moved. But we're just going to call it distance. But this is a horizontal distance. If it's horizontal, it's called x because of the x-axis in a graph. Right? So horizontal is x and the y-axis is vertical. So this can also be called delta y if it's vertical. So delta x is for horizontal and delta y is for vertical. And both of these are given in meters. Okay, those are our variables. Now with our variables, we get a group of equations. So the equations are the following. We have v equals vo plus at. We have v squared equals vo squared plus 2a times delta x. We have delta x equals vo times t plus 1/2 a times t squared. And we have delta x equals v plus v0 over 2 times t. These are our 4 equations. So anytime you get a problem about motion, you're going to have to choose one of these 4 equations to use. So that's where most people get confused. They have a problem and they don't know which equation to choose. So what we can notice here that is going to help a lot is that each of these equations has 4 out of these 5 variables and is missing one of the other variables. And that's going to help us determine which equation to use. So in the first one, we have v, we have v0, we have a, and we have t, but there's no distance. So this equation does not include any delta x. This second equation has delta x, and it has v, v0, and a, so it has this one, this one, this one, and this one, but it doesn't have time. So this equation has no time. This third equation has time. It has initial velocity, delta x, and acceleration. So it has this one, this one, this one, and this one. It's missing final speed. This one has no final speed. And the last one, it has final speed, initial speed, time, and delta x. It's missing acceleration. So this one has no acceleration. So notice that all of them have initial velocity, but the rest of the variables, there's one equation that is missing that one. Now there's something else that I wanted to mention. We're going to be using things that are moving either horizontally, which means to the right or to the left, and things that are moving vertically, up or down. And we're going to use the following notation. So notation is that we all agree on something. Because graphs look like this, the positive x-axis, the direction in which x is positive, is to the right, right? To the right of the 0. So this is 0. To the right is positive x. And to the left is negative. That's what you get on a graph. So we are going to take that notation and we're going to all agree that if we're given a distance or an acceleration or a speed to the right, it's going to be positive. So to the right is positive. Positive. And to the left, if anything is to the left, it's negative. So for example, if I tell you it had a speed of -12, the meaning of that negative is just that the person was going at 12 meters per second to the left, because left is negative. And the same thing happens with the y-axis. If it's a vertical problem, up is positive. Because of the graph, y is positive upwards and negative downwards. So if it's right or up, we're going to say it's positive. If it's left or down, we're going to say it's negative. So that is the notation that we're going to use from now on when we're solving problems. And the last thing before we try an example is a list of tips that can help you. All of the equations require 4 variables, and sometimes you're looking at the problem and you can't find the 4 variables. So that may be because it's hidden in the words. So there are some words that the problem might say that mean something about these variables. So what do I mean? Sometimes the problem is going to say starts at rest. So it's going to say something like a car starts at rest. As we learned before, at rest means that it's not moving, that it's staying still. So starts at rest means that the initial speed of the object is 0 because it's not moving. So we can basically translate starts at rest to our v0 is equal to 0 meters per second. We can put that as soon as we see starts at rest. It might also say comes to a stop or ends at rest. Comes to a stop. Comes to a stop means that at the end of whatever journey it's doing, it stops and its velocity is now 0. But it's not its initial velocity. It didn't start at rest. It ended at rest. So we can say that the final speed v is 0. That's what we can translate that phrase to. If it's any vertical example, so something is falling or something is being thrown upwards, it's one of the cases of what we saw last class, acceleration due to gravity. So anytime that a problem is vertical, they don't need to tell you the acceleration because we already know, we found out last class that the acceleration will be equal to 9.8 meters per second squared. But today we learned that anything that is going downwards is negative, and the acceleration is pulling everything downwards. So we're going to use now negative acceleration, because negative means down and the acceleration is pulling things downwards. Another thing is that if it's an example for vertical and something is thrown upwards and you're being asked for the maximum height, as I had told you before, at the maximum height the speed is 0 because it stops for a millisecond and then starts coming back down. So if we're being asked for maximum height, the final speed is 0. Because the speed at the moment that it reaches that height is going to be 0 as it stops momentarily. 0 meters per second. So basically the final speed will be 0 either if it says comes to a stop or if it says maximum height. And finally, if an object comes back to its original position, it won't have any displacement. It will begin and end at the same point. So that change in position will be 0. So if it returns to the start, so returns to the start, what we have is that there is no delta x, so delta x is 0 meters. Right, so these are our 5 hints. And that's it for the theory. So now I want to solve a problem using all that we have learned. So I changed up the board a little bit to put the variables here to the right so we can use this space to solve the problem. So the problem states the following. You have a car moving to the right, at 15 meters per second. Then it starts accelerating at 1.2 meters per second squared. What is its speed? After it has traveled 3 meters? So you look at this problem and immediately it's not obvious which equation to use or what process to do. So this is where I'm going to tell you the recipe for what to do. So what I do first is write a list of my 5 variables so that I can fill in what each of them means. So I'm going to have to find an initial velocity, a final velocity, an acceleration, a time, and a distance, right? So I write my list of variables and then I look for them in the problem. So I start reading. Car moving right to the right. Oops, to the right. To the right means it's positive because of this notation. So a car moving to the right at 15 meters per second. If you don't know if that's a time, a speed, a distance, you can look at the units. Meters per second has to be either initial speed or final speed. So 15 meters per second is our initial speed. So here we found our initial speed and we can put it in here. So V0 is going to be 15 meters per second. Okay, now let's continue reading. It starts accelerating at 1.2 meters per second squared. So here we found another value that is going to help us, and this one is in meters per second squared, which is the unit for acceleration, and it says accelerating at, so this is our A. Right, so we can fill in our table, in the acceleration put 1.2 meters per second squared. We keep reading. What is its speed? What is its speed? So there we're going to find what we're being asked for. What is its speed? This is final speed because we already have the initial speed. So final speed is what we're being asked for. I always put a question mark so that I remember that that is what is being asked for. And after it has traveled 3 meters. So if this is in meters, it has to be a distance. So this is delta x. And I can put that here. Delta x is 3 meters. So what variable was not mentioned at all in the problem? Time. Time is not mentioned, we're not looking for it, and we don't have it. So we can say, okay, no time, no time, and we look for an equation that has no time. So this one has no distance, no time, no velocity, no acceleration. This one is the one we need for this problem. The second equation, the one that has no time. So that's our third step. So first step, write down all the variables. Second step, identify them in the problem and write them down beside their name. Third step, find the variable that is not mentioned at all. Not the one that we're looking for, but the one that's not mentioned. Cancel it and find the equation that doesn't have that variable either. So we picked this equation. V squared equals VO squared plus 2a times delta x. And now we start putting into our equation all of our variables. So our v, we don't know it. So we're just going to leave it as v because that's what we're going to solve for. V squared. Our V0 is 15 meters per second. So we put 15 and it's squared. Plus 2 times. What's our acceleration? 1.2. So here we put 1.2. Times, what's our distance? Distance is 3, so we put here 3. And this we put into the calculator. This is just a number. So what we're going to get is v squared equals 232.2. And this is almost our answer, but since we have v squared and not v, we need to solve for v by taking the square root. So our v is the square root of 232.2. And this is equal to 15.2 meters per second. And that's our answer. This was what we were looking for. The question asked, what is its speed after it has traveled 3 meters? Its speed is going to be 15.2 meters per second. Right? So that's how you answer a problem of these.